Bring up this is where we really start picking up things that we can't do with motor controls. It literally in motor controls with relays we can't do counters. So what they do is they buy counter units, and then they can read from that. They can do timers. We actually pass some timers around. But one thing that we can't do with relays, we can't do what? Math. But these are not relays. These are computers. And computers can definitely do what? Math. So we'll look at our math instructions. And we'll go back and review the ladder logic rules. So we're going to look at an add instruction. We're going to look at subtract instruction, multiply, and divide. And I think that's the only instructions that the lab book talks about. But you should realize that it's a computer. It's kind of like a calculator. So just about any math function that you see on a calculator, we can do it eventually in a PLC, right? So rules, input instructions on the left of the rung. Of course, in relay logic, we call them control devices between L1 and load, right? Output instructions on the right, one input per line. Input devices can be connected in series parallel and series parallel. Output only what? Parallel. Input addresses can be duplicated. Output addresses cannot. And I put this in red because I know we could used to do this, but I'll go in and check it once I connect the one down the Bradley PLC. Used to you could duplicate them, but you had to do what? You had to do the entire run. Yeah. Of course, here I try to combine relay and PLC. So there's some things we do in relay that we do in PLC, especially when it comes to line numbers and stuff like that. Input and outputs must be placed horizontally. This is definitely true in PLC. Signal flow must be what? From L1 to L2. So we can't have any backflow. Diagrams must be numbered and commented correctly. Relay logics, we do the rung numbers are on the left, right, you understand. But in relay logic, we don't use rung numbers, we use what? Line numbers. Yeah. Instruction symbols are placed above the symbol. This is true for relay logic and sort of. Relay logic, if the symbol will fit inside if the name will fit inside the symbol, we put it in there. So normally motor controls will see that, but if the name won't fit inside the symbol, we usually put it above it, right? Location of coil contacts, and this is only true for what? Relay logic. So one of the advantages we get on relay logic is that it's got those contact of the numerical cross-reference numbers, and what does those do?
It shows you where
each contact's at, right? So we can follow it real easy. Program controllers, these are terms. Program controllers are digital computer used for automation of typically industrial electromechanical processes. Y'all can read that as good as I can. In computers, this is what an instruction is. Is everybody okay with an instruction? This is a program in computers. So all of these are relative to PLCs and computers. Are y'all okay there? And of course, this is what you are. You're what? You're a programmer. Operand, we talked about these. You're going to run into these all through, even in this textbook, and especially in PLC manuals. So any instruction that operates on a number, the number that is being operated on, we call that the operand. Y'all understand that? So if I add two numbers together, the two numbers I'm adding together are what? Operand. And the answer is a what? Is an operand. So any numbers that an instruction operates on is called an operand. Everybody okay? You're gonna run into that in this textbook, and the guy don't even put it in his glossary about that. But that's what an operand is. Integer. Everybody okay on integers? And these are relative to PLC. So what's an integer? Well, an integer is an integer. What is an integer? It's a what? A number without a fraction. So we can represent integers extremely big, but what we do in PLCs is we're going to limit this to a certain number of bits, right? You understand that? So what we can do in integers, and we'll look at that next, depends on the number of bits, depends on what our range are. Our integers are signed numbers. And it uses that little thing we call 2's complement, which is kind of weird for us, but basically what you do is you can take your total number of combinations and do what? Divide it by 2, and then take away 1 from the positive number. Floating point numbers, these are signed numbers that have a fractional component and use as scientific notation. So floating point numbers are going to be rounded, right? There's going to be a lot of rounding that takes place if you exceed the range of the number of bits, and scientific notation starts rounding. Absolute value. These are real numbers that regardless of the sign. So an absolute number is considered to be positive no matter what the sign is. So this is what happens on our PLC when it uses signed numbers. If you exceed the range, then you lose the sign. So we probably noticed that when we were counting with our counters, even though it went up past the range of signed numbers, the counter kept counting. But what we end up with is we end up with an unsigned number out of that. But we get an indication. Y'all remember what the indication is if you exceed the range?
Oh, what do you call what?
We call them overflows. So we have a bit inside our status register or inside our flag register that indicates when you exceed the range. So on an up counter, we have an overflow flag. On a down counter, we have an underflow flag, right? The counter will keep counting, but what happened is you just screwed up. You've lost the sign, right? Arrays. Arrays are a group of operands stored in consecutive memory addresses. So later on, we'll start dealing with arrays. Which is really good. You okay? Any questions so far? By the way, if you're looking at this on Blackboard, I just was updating this morning, so this hadn't been uploaded, but I'll do this tomorrow. Scientific notation. A method representing very large and small numbers in terms of a decimal number multiplied by a power of 10. So we take a number and then we multiply it. So I say times 10 to the, that's the way I talk about scientific notation. This is scientific notation. So floating point math uses scientific notation. Okay. Okay. Now we learn a version of scientific notation called engineering notation. Basically, it's scientific notation, but the power of 10 has to be divisible by what? By 3. Yeah, so this is not engineering notation right there. This is just scientific notation. So scientific notation would go 10 to the 0, 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the fifth, or 10 to the sixth, right? And of course, if I was going on the other side, it'd be to the -1, to the -2, to the -3, to the -4, to the -5. So scientific notation uses all those powers of 10. But when we go to engineering notation, we move in groups of what? Yeah, so we go 10 to the 0, and then we go 10 to the third, then we go 10 to the 6th, right? Then we go what? 10 to the 9th, right? 10 to the 12th. If I was going on the other side, it'd be 10 to the -3. You can only have one 10 to the 0, by the way. It would be 10 to the -3, right? 10 to the -6. So it's just a form of engineer notation, but instead of using all those powers of 10s, we move in groups of what? 3s. A variable, a constant. What is a constant relative to programming? We've talked about this though. Without change, it don't mean you can't change it. It just means you can't change it without changing the what? The program itself. There's very few constants, true constants in PLC. Like in math, we have pi, right? Would be considered a constant, and you cannot change pi.
Yesterday was pi.
You can round it, right? But you can't change it. So we can use any constant that we deal with in PLCs can be changed, but you have to do what? You have to change the program. Now, what's a variable? Yeah, we can change the number without changing the program, right? And we're going to simulate that a little bit. Integer ranges. So integer ranges, we learned back in earlier. This is what you learned in Intro PLC. That we use a technique called Who's complement. So what happens if I've got 16 bits, I get 65,536 combinations, right? You understand that? Well, what we do is we sacrifice the most significant bit for the sign bit. And as soon as you do that, you only get half the number. And of course, why do we have one more negative number than we do have positive? Got 0 eats up one of the positive slots, right? Now we can shift to word. Word, if we use the whole word, then we get this range. Okay, does that make sense? But to use words, what you have to do is you have to get into the PLC status register, and you have to set bit 14. And we'll show you how to do that. So if you set bit 14, then it's going to deal with words. If you don't set bit 14, which is the default, what does default mean? Or what it uses if you don't tell it what? Something else. And that's what computers, we use the term default all the time. So computers have got to know things, even if you don't specify it. So just about every computer, if you don't specify, it's going to use somewhat. It's going to use some default. So by default, this status bit, the S2/14 status bit. So y'all understand that? They called it the S2 register, but it's the only status register we have. So really, inputs, technically inputs, if you look at what data file it uses, and we could use this too, is this is the actual syntax for a data. So I'd say I, and then I'd say 0, colon, so that's supposed to be a 0, guys. And then I would say maybe 1/1. Well, and then if I wanted output, output is truly output, colon, 1/1. Well, what it is that we've only got one output register and we've only got one input register. So what does Allen Bradley don't require you to use? You don't have to put the 1, you don't, because that's the only thing you got, right? You understand? It's not like the B3 and the B10. So if I want to switch between those registers, I have to specify another data file, right? This is also true on the status register. If you look at the status register, it's actually an S2. It's S2. It's at this location right there. If we went back and looked at last thing, but we've only got one status register. So what does that mean? Yeah, you don't have to put the 2, right? So it takes that by default. So if I say S colon 2/14. Then this is going to be the second word in the 14th bit, right? Does that make sense? And if you set that bit, then when the next math operation you use is going to use 32 bits. If you don't set that bit, then the next math operation is going to do what? It's going to use 16. So this is the way in the Allen Bradley PLC that we specify a what? A word or a long word. Siemens, you actually put it in your instruction. So you use B for byte, you use W for word. So you actually change the instruction with it. Okay? So if I use 16 bits, I get a range of 32,768 to plus 32,767. If I set bit 14, then that gives me 32 bits, and it gives us numbers in this range right here. It's a pretty good number, right? And this is if you, but in this one you have, but what you got to remember is that if you set that bit, every address you specify it's gonna automatically grab the next address. So what we're saying, I can't use N70 and store a 32-bit number in there and then my next number stored in 1, right? You have to remember that you got to do what? If you're going to use this 64-bit math, 32-bit math, you're going to have to remember that every answer is going to be what? It's going to occupy what? 2 addresses. Do you understand that? So floating point, good, gracious. Look at floating point. Here we're going to start rounding, just like your calculator. So in your calculator, when you exceed the range of your calculator, it will automatically switch into scientific notation. As soon as it switches into scientific notation, then numbers are going to be rounded, right? Y'all understand that? Yes or no? Yeah. So numbers are going to be rounded. They're not going to be perfect, but they're going to be perfect enough or close enough. All right. So this is our range right here. Depends on whether you use 32 bits or 16 bits. I think this is 64 bits. I think this is 32 bits. I'll have to go back and look. And since it's scientific notation, you're going to lose at least you're going to lose that number anyway, right? You understand what I'm saying? So we don't lose that one positive. We don't lose that one positive combination. But if I'm going to use floating numbers, then we got to use this data file right here, right? FA, which the book, when it tells you about the data files, it mentions D3, but it don't mention what? FA. But then in the math instructions, it says you can use FA. But y'all know the FA is for, that data file is dedicated for what? Floating point number. So if I'm using integers, then I'm going to use what? N7. If I'm using data files, I'm going to use what? FA. Now, it depends on the PLC. Some of our PLCs have 2 integer files. They have the N7 and also they have the N10. So these are in that. How many you have available? It's just like some PLCs have a B3 and a B10, right? You understand that? Some Allen Bradley PLCs they all have a N7. Some of them has a what? An N10. And it all depends on the PLC. And I don't know, I would look at the 1100 and see what they got available to it, but I'm not. So N7, by the way, if you set this, then this is going to dump into 32 bits, right? I think it's already 32 bits. I need to research that a little bit. So here's our registers. So we have 0, right? And that's what we're talking about. So outputs are actually file 0. But we don't have to understand that because we can only have one of them, right? So the 0 is understood. So I got that backwards logo there. So outputs is what? 0. Inputs is what? 1. S2, this is your status register, but you've only got one status register. So on all 3 of these, you don't have to put the file number, right? That makes sense. When you get down to here, you do. Yeah, so B3. Now here, this is kind of misleading too. What does it say we use? And a lot of y'all answered that. But it says the B3 is used for what? You think we can use that thing for other things? Yes. We'll look later on sequencer shift instructions. So we have several instructions that can use the B3. And we'll learn that as we go through here, what other uses we have for the B3. And then we'll come back, or the B10. So remember, when I say B3, I'm also talking a little bit about the what? If the B10, if it's available on your PLC. Timers, by default, is what? So B is bit. Timers is what? Default by what? 4. Counters, default is 5. C5. Control register, you got to specify this. R6. And integers are going to be N7 or N10, and we might have an N10. And floating point is going to be FA. Now, if there's another one for floating point, I'll look at it. B10. It looks like we can use that for either integers or, we'll look at that. Everybody okay? And then all these other ones are what?
Fine.
Yeah, these are user defined, so it means you what?
You define.
Yeah, you define them. So I might come up and use like an F22. Well, an F22 would define that register as a what? A floating point register. Right? You understand that? And how many of these are available will be determined by your PLC. Everybody okay? Lost anybody? How many times have we looked at this one?
3 times.
3 times. These are the math instructions supported by RS Logic 500.
Is this on Blackboard?
This one is, but I've added some things. We've added some things. Yeah. But this chart, by the way, is this on Blackboard? Yes, it's on Blackboard. But where is it? Well, what you need to understand is you probably need to start looking at the actual manual that comes with the PLC. So what we've done on Blackboard is we've actually placed the manuals that come with the PLC. And these guys are usually free. So that means you can go in and you can type up, Micrologic 1100 user manual, or just type in Micrologic 1100, and it's going to pop up all these PDF files of all this stuff that Allen Bradley gives away free. Now, why do they give them away free? It have increased sales because now an engineer's going out there and trying to figure out, and they give these manuals away free, then it's a high probability that they'll do what? Yeah, that they'll buy it from them. So what we have is inside Blackboard. Oops. So inside a course content, and inside, no, it's not in course content. It's in reference material, sorry. Right here it says what? PLC manuals. And then I can come up here, and then I got not only the manuals for what? Allen Bradley, but also the Siemens we have. And then I could come over here and look at the user manual. And then I could come down here and look at math instructions. And where did I get this chart from? Right there. So, I try to clip them into my PowerPoint, but you've got access to this that tells you everything you need to know about this PLC to be able to do what? Programming. So, this is where I pull this out. So this is the 1100 PLC. I think. So this guy supports all these math. Now the book covers is add, subtract, multiply, and divide. And then clear, I think it covers clear. But also square root, we can do some scaling data, ramping data for like SCR drives. ABS, the book does color ABS, and what's ABS? Absolute value. So what means that would take a signed number and convert it over to an unsigned number, right? You understand that? Then you get into swapping, you swap it around, you can start dealing with trig, arc sine, arc cosine, arc tangent, cosine tangent, log, sine tangent, and raised to the power. So these are the math instructions that's supported by the 1100. Is this all of them? Well, probably not. Right, so the number of math instructions that's available to you would be determined by what? The PLC, right? The PLC that you're using, and it'll pop up. So this is one of the things you do when you come up there and you start RS Logics and you create a new project. The first thing it wants to do is for you to select a PLC. A CPU. And what do you think you're doing when you select that CPU? You're bringing in what? The instruction set for that CPU, right? You understand? So that's what's really neat. So when you go up to that taskbar, that instruction bar, and if it's not up there, it means it's not supported by that CPU. It don't mean that Allen Bradley don't support it. It just means it's not supported by that CPU. Because the more functions they put into it, the more complex it'll become. And then it's just like robots. So robots, they got tons of instruction they can put into a robot computer, but why would I use welding? Why would I need the welding instructions that would eat up memory that I'm going to use for my program if my robot's never going to do what? Weld. So that's one of the things when you buy a robot, you need to specify what the application is, and then when they give it to you, it would have the instructions that's required. I think we've only got one welding robot over that's got it in there, and that's the Motorman robot. Of course, the weld shop, they've got a Fanuc robot, and that robot's got all the watt in there. It's got all the weld instructions. Did y'all get to play around with that? Well, that robot's been over there for. No, that robot's been over there for. I don't know where it's been.
Like somewhere.
That robot has been. That robot came in about the same time we got ours. So they've had theirs. All right, okay. Most of these you use in math. I don't know if you take AC, you'll get into these sines, cosines, and tangents. There's several classes that will deal with logarithms. These allows us to deal with angles and arcs and all kinds of stuff. This right here is a really, really neat instruction that the book does cover, and we'll look at this. So what this does is that you can actually put a math formula in. Basically, you make the PLC do just about any math you want it to do. So you just type it in, and we'll show you. Are we okay? So, words and bits, we okay with that? Each storage location in the PLC consists of 16 consecutive bits. Memory locations can be combined to handle numbers greater than 16 bits. And we looked at that. It looks like the limit on this application would be 32-bit math. But your new PLCs usually support greater than that. So a bit is a single binary digit. Everybody okay there? A nibble is a group of what? 4. A byte is a group of 8, starting with a least significant bit. A word is a group of 16. By the way, the minimum on Siemens, they go in bytes. They don't go in bits, they go in bytes. And these for every group of 8 bits, you go to a different word, right? Not a word, another byte. Double words in Alabama and Allen Bradley PLCs are what? 32, and then quad words, which these Allen Bradley PLCs we have don't directly support that. These are what we're going to be discussing here. So an addressing mode, was that back in the definition? Well, an addressing mode is the way that we tell the PLC or tell the application how we want to address these operands. So in these labs, we're going to use the first two, and it's called, so the first one we got is called immediate addressing. And what does that mean if I use immediate addressing? Yeah, the actual operand is a constant, right? It's going to be inside the instruction itself. That makes sense. So the operand will be part of the instruction itself. Okay, does that make sense? I think the first example they put is this guy right here. So it says add. We'll look at it. So basically, an add instruction is made of 3 things. We have 2 operands, right? So we have source A, source B, and then our destination. So this will be our sum. Well, none of these actually has the number. What do they have? They have a register. They have a register address. They have a data file address. So what this means is that these wouldn't be what I would use for constants. This would be a type of addressing mode that I would use for variables, right? You understand? Yes and no. because I'm not putting the number inside the instruction. So if I came over here and I said, if I came over here, I'm just going to mark this out, and I put 320 out there, then that is the number that I'm adding together, right? I'm adding 320, but what am I adding it to? Huh? Source B, but where is that operand at? No, it's right here. So, I mean, I would have to go out to N7, 1, and inside here would be my other number, 562. Okay, you understand? So what this does, this is not the operand, it's pointing to the operand, and the operand is out in an address somewhere, right? You understand? And a data file. Okay, you understand? So here, this 320 is actually part of the instruction. If I wanted to change this, I would have to change the instruction, right? You understand? If I wanted to change this one, then I'd have to change the contents of that address. Now, how can the contents of this address be? I mean, it could be the results of another math operation. It could be brought in from inputs, right? You understand that? So that would be considered a what? A variable. Does that make sense? Okay, because we can change that without changing the what? The program. So this would be an example of what we call direct addressing. And direct addressing, if you say, I'm giving directions to where the location's at, then that's what direct addressing. So immediate means the operand is what? Part of the instruction, right? You understand. Direct addressing means I'm giving directions to where that operand's at. And that's all these other addressing modes, you're giving directions. So these are the two that we're going to be using in lab right here. We're going to be using immediate and direct.
So direct roughly C1.
That's right. So you could pull it from the accumulator. You could pull it from the accumulator of a timer. So I could bring it in from the accumulator of a timer. I could bring it in from the accumulator of a counter. Right? You understand? And while I'm counting, those numbers are always changing. So anything that's addressable, we can get to. The only thing that we can't get to is your inputs. So if I was going to use an input, then if I was using an input word, then I would have to bring it in with a move instruction and in place of integration. That's the only difference. But because that's considered outside stuff, right? You understand? So yeah, we could bring this in from a thumb wheel switch. We could bring it in from push button. We could bring it in from, like you said, the results of a previous math operation. We could bring it in from the accumulators of a counter, or from the accumulators of we could bring it in from the preset of a counter, which basically could be a variable too. You know, I think we showed y'all how we could use that as a variable too, right? So the preset on our counters, we were using constants, right? Or we was using immediate addressing. Okay, so that's a good point. We got another one called indirect addressing, which we're going to look at later on too. Indirect addressing says the specified register address. It's not the operand, it's the address of the operand. So how would that work?
Telling you where to look.
Yeah, that's what it's doing. It's not actually the operand, it's just telling you where to look for the operand. So that's why it's called indirect addressing. So we're not getting the operand from that address, we're getting it indirectly from that address, right? And we'll look at that too. So we'll look at that later. And then we got another addressing mode when we get into our really advanced instructions called index address. When we get into what we call our stack and setting up tables and stuff like that. This is an address of the operand specified by the contents of the register called a what? Index register. And it's what? But what we're going to do is we're going to do what we do. Add an offset. This is the way, by the way, this is the way you specify inside your instruction. If you want to specify indirect address, and you put it inside what? Bracket. If you want to specify indexed address, and you start it with what? With a number sign. And then it says no. I go, huh? Yeah, hold on, let's get through this slide. Then it says indirect addresses can be used, indirect addressing can be used if not supported by the PLC by incrementing and what do we mean by incrementing?
Incremented to echo up.
Yeah, but every time we increment, it's gonna go by one, right? And then decrement means every time we decrement, it's gonna decrease by one, which is pretty neat. So we'll see how we can do that. We'll use these in the math lab assignment, and then these guys right here, we're gonna do this way. Now, where can you find more information about the addressing modes supported by a PLC? In the manual. So you just go in there, bring up the PDF file, type addressing modes, it'll pop up and it will tell you all the addressing modes supported. So every PLC is going to support these different addressing modes. And what it does, it adds more power to the way you address these operands, right? We can point them, we can move them, we can increment an address, we can move around, we can scan through tables. We use tables a lot. We'll do this especially when we get into sequencers and stuff like that. We can save stuff automatically. It's really, really neat. When we set up something called a stack, where we can save stuff and then pull it back off real easy without, specifying a lot of addressing. So we can scan through tables. We use tables all the time, right? You understand that? Like the ASCII code chart. Well, what is ASCII code chart? It's just a table, right, that you go in and look things up. And so we do that all the time where we can build tables inside our PLC, like tolerances and stuff like that. And then, the PLC automatically pulls from that table and it might do that 5 or 10 times. But all I have to do if I need to change those tolerances is not go find all those instructions, just go in and do what? Change the contents of the table. Okay, guys, I'll take a 5-minute break.
When you talking about parameters.
Yeah.
Parameters
Or if we have conversion factors that our plant uses. So we have different conversion factors. Well, instead of me trying to come up with them, I can put those conversion factors in a table. And then every instruction that needs those conversion factors can pull it. But then I can do what? I can go in and change the table without going in and
I understand that. I've been in those scenarios like that.
Yeah, where you have to go to a table.
Yeah.
Yeah. So anytime you got to go to a chart and you got a list of things.
That was a account manager's.
So everybody okay on how to address these inputs and outputs?
Yeah.
Well, by the way, if you come up and you leave off the dot, this is something we haven't done now. What's it going to do? So here I come over here. I don't specify a dot. I just go up there and put 1. I don't specify anything past that. And what's it going to do? It's going to bring in all 16 bits. Okay, man. Yes or no? And if we use an output colon 6, this is going to output, right, all 16 bits of slot text. So you can output a whole word at one time. So later on, we'll pick up an instruction called a sequence. What's so neat about a sequencer is you can set up any pattern of outputs you want it to go into. And then all you do is you just save that whole 16-bit pattern into an output port and all 16 on the chain. So if we wanted motor number 1 to start, then number 2, and stop number 3, and start number 4, and move this guy, shift that guy, and we had the sequence of events that we wanted our line to go through, you can set it up in a sequence. It's really, really neat. What we can do is we can output a whole bit. Now, it's kind of hard to do this on our PLC because we've only got 8 inputs and 8 outputs, right? But we can look at it on Logic Pro, because it gives us a lot of inputs and a lot of outputs. So this is the floating point math, and it's basically the same thing. Floating point number. It's the same thing as the the layout of the instruction, but it's the same thing. So what, you did what? L. Now we're using A, but then you got all those other addresses out there that says what? User defined. Which means, so F8 is fixed at the floating point math register, or data file, right? But if I need more floating point math, then I can use one of those other guys out there, like an F22. As soon as I say F, then it assumes that that data file is floating point, right? If I wanted more integer registers, then we can use like N37, right? If the PLC has enough memory. But right here they say F, and what is F? The file number. Number 8 is the default. A file number between 9 and 255 can also be used for additional storage if required. So those out past 8 are what? User definable. Right? You understand that? Operands. So this is the add instruction. 2 operands hold in what we call source A and source B, which are added together. Either both sources can be registers, or one can be a register and the other can be a constant. You cannot use 2 constants, because that would be stupid for me to use an add instruction to add 5 plus 3 when all I could do is just use the number 8, right? You understand that? So we're not going to use an add instruction to add constant. One of them could be a constant, but the other one has got to be a what? A variable. Y'all understand that? Now the destination has got to be the address of where we want to put that at. So the destination has got to be an address, right? You understand? Everybody okay? Okay, Christine? So 3 operands. What's the 3 operands? The 2 we're going to be adding together. That's source A and source B. And then we're going to specify a destination address where we want to put our answer at. Everybody okay? So this is an example of an add instruction. Here they're using, in this example in the textbook, they're using direct addressing, right, on both of them. So whatever I put into address N70 is going to be added to whatever I put into address N71, and it's going to store it in N72. Everybody okay? This is what we call direct addressing. And later on, so when I specify direct addressing, I don't put the operand, I put where the operand's at, right? You understand that? Does that make sense? And all the rest of them are the same, guys. These are our status bits, so we get inside this S2 register. But you don't have to put 2, because 2 is what? Understood. Yeah, it's understood. So I have a carry flag set when there is a carry in the add instruction or the bar instruction, borrow, not borrow. That's my southern. Borrow instruction in a subtraction, right? An overflow. What does an overflow tell us? When you've exceeded the range of your sign numbers, right? Everybody understand that? It don't mean it's going to give you. So what it's got you up there, it's going to give you an answer, but that answer is you're going to lose the sign. Everybody okay? 0. What does this tell me? It tells me if the results of the operation is a 0. So if you come up and you added 2 signed numbers together, so if you added this plus this, you're not interested with the answer. All you're interested in when it subtracts or adds down to 0, right? You understand? By the way, I know y'all can subtract by addition, right? So one operand is positive, the other operand is negative. If you add them together, then basically you're subtracting. So if you use subtraction, what's it going to do? It's going to change the sign to the second one and add in. Y'all know that, right? And then this guy tells us the what? The sign that tells us if our answer is what? Positive or negative. These are inside this status register. So this is the first time we used it. Your timer, the flag is part of the timer instruction. That timer timing, timer done, timer enable, that's part of the timer instruction. So if you want to address those status bits, you'd say what? You'd say timer forward, 0 done / done, right? For your math instructions though, you actually have to address the status register. So you'd have to look at S0 / 0 is going to tell you what, if you had a carry. S:0 / 1 would tell you if you got a what? An overflow. S0 / 2 would tell you if you got a what? 0. And S0 / 3 would tell you if you end up with a negative number. Now, the sign of the number. So that's the way you would address it on your, if you're going to use it with an input, you would address it like that. Instead of saying timer 4, you'd say S2 / 0, right? Or /1, right? You understand that? Yes or no? Go ahead.
You won't answer it.
No, we would come over here and, this is just real fast, guys. Yeah, we'll do it right now. So if I got 2, and I come over here, and then I come over here, and I come over here and add those 2 numbers together. And I'm not going to put the registers. And then down here, I want to turn on the light if it came up to be 0. Well, I would come up here and I would look at the 0. So what's a 0? Okay, so down here I would use that address. I'd put S:0 / 2, and then I would come over here and I would turn on the light, and then I'd use an output port to turn on the light, right? So what we're doing now is if after my add, if it caused a 0 answer, then I want to do something about that. So basically we're doing the same thing on like the T4 / done, but on the counter, the done bit has a name, right? You understand? The enable bit has a name. These status registers, you actually got to specify the location of the bit that your instructions is interested.
Yeah.
I follow that. All that makes sense. I'm right here. I'll do a program with more than one add. How is that status?
Well, it's going to be according to the last add instruction you did. So if you want the status of this first add instruction, then by George, you better check it after that add instruction. And then you would check it after the next one. Understand? Yeah. So yeah, you just can't add 15 numbers together and put and then examine the status bit down here, right? You understand? Well, I want the status bit for this first add. Well, it's going to give you the status of the what? The last add. So you'd have to put it, y'all understand what he's saying? What Anthony's saying? So if I came over here and put another add instruction, and then if I wanted to look at that flag, I would have to come in here and do what? I would use that same address, but this would give me the status of that add instruction. This would give me the status of that add instruction, right? And of course, if I wanted to save it, then I would have to save it before the next add instruction. So these guys do these instructions one at a time, right? You understand? So we can examine the status register. Well, if I wanted to save the status of the first add, then what I would do here, instead of using an out, what would I do? I would use a move, right? And then I would move that status. I could move the whole status register somewhere else and then use it somewhere else if I needed it. If I wanted to take care of all my adds, right? Does that make sense? That's a good question. I think that's the first time it's ever came up.
That's a subset?
Huh?
Subset?
Yeah, so what we could do is we could take the whole status register if I wanted to move it. All right, so I could come up here, and of course I know I've got a mess up here and it's hard to see, guys. Of course we're going to waste a byte, but up here what I could do is I could say move, and then my source would be my status register S:0, right? You understand? And then my destination would be where I wanted to put it at. Then I could say, like, my destination would be, like N7:4 or something like that. And that, what you've done is you save that status register, and then you can save the status register of the next add if you didn't want to use it instantly, right? You understand that? And then when you got through with all your adds, then you could examine and say, okay, was this one 0? Did this give me a 1? Did I have a carrier bar? You could do that with other instructions. So that's a good question.
Christie, but I'll ask anyway. Tell me if this is right. Essentially, I wasn't understanding why what exactly are we adding? What is the end result? I understand what you're teaching me, but I didn't know why. So if you have two counters together, okay, I know it's in my head, but I can't.
The example they're using in the book is I'm feeding a main conveyor. I'm feeding a main conveyor to 2 conveyors. And what I'm trying to do is I'm trying to keep a total count. Well, when they get down here, it would be impossible to count them, right? Because they're side by side. But as they're coming in here, I could have a light sensor going across here. And every time this breaks it, this is going to take 1 counter. And then over here, when these come through, this is going to be another counter. Right? You understand? And then what we do is my instruction, I would come up here and I'd say add the accumulator for counter. So if this is counter 1, then my add instruction would be add, right? And my source A would be counter, I'm just going to put counter 1. My source B would be counter 2, right? You understand? And then we're going to put it somewhere. We're going to put
So these other things are just basically formulas in case you have a number that's negative or a number that has a fraction. Is that what you're saying?
What do you mean? The
When you're
flags.
saying, okay.
The flags would be if I didn't care how many I've had, I just wanted to know when this and this took away from each other, I ended up with 0. So instead of me trying to compare and all this kind of stuff, I could just look to see when the output of my math went to what? 0. Or if I exceeded the range of my numbers, and I'm going to have to do something if I exceed the range of my numbers, because what happens is all of a sudden, if I've got an overflow, guys, you've got an overflow. So I mean, you've counted up to 65,536, right? You understand? And you add one more. Well, what's the thing going to do? Well, I'm sorry, 65,535. It's going to roll back around to what? To 0. You're going to lose your whole count unless you can figure that. Okay. I got an overflow. Well, what you can do now is you can stick that number somewhere, right? You understand, and then let it roll around, right? And stuff like that. So you can exceed the range of numbers real easy. It's just that you got to have an indication when this thing, something went wrong, right? You've exceeded the range. You've exceeded the range of your signed numbers. You've exceeded the range of your numbers altogether, right? You understand? So if I'm using 16 bits of unsigned numbers, the biggest thing I can have is 65,535. So used to in the old days, our car odometer, anybody got an old car? It went up to what? And then once you went past that, what does it do? Don't give you an overflow, just rolls over. Now we add that other digit, so now we have to go a lot. It's a bit 999,000. So there's very few people that roll the odometer over on a car anymore. And used to, you could literally, before they figured that out, you could literally jack your car up and run your car in reverse and the odometer would go backwards. But they finally figured that out because the people selling new cars would do that.
What you said about the second phone? So we said the first instruction was to that.
Well, the second would go to the same S register, and that's what Anthony was talking about. So what he was saying, he says, what if I had multiple add instructions? What happens to the status register? Well, the status register is going to tell you what happened with the last add instruction. So what we were saying is that if you need that data before it hits the next add instruction, you need to do what? You need to save it. And you can, because remember, it does what? It does inputs, logic, outputs. And then it does what? Then it goes to the next run. So all you got to do is just save it before the next add instruction, and you'll be fine. Just make sure the rung is between the two, right? Yeah, with the move instruction. I don't know if you can see what I did right there. So what I did is I moved the status register 0, which is your flag register for these, and then I put it in N74, but you could put it anywhere else.
That,
Yeah, the source is the status. I pull in the whole 16-bit register. By the way, what we would do, and we'll learn that later on, is we would mask it off. Masking allows us to strip off bits that we're not concerned with. So S0 is a 16-bit register, right? But all I'm interested in is what? 0, 1, 2, 3. So what we would like to be able to do is what? Get rid of those bits that we're not interested in, because they're going to bring in something, right? And later on, we'll learn about masking. We got to move with a mask, so you can actually strip off the bits that you don't want with one instruction. That's pretty good. Good questions, guys. Now we're okay. Every instruction now is the same, right? You understand? So subtract. What do I got? I got 3 operands. I've got what? A source A and a source B. Constant. We can have a constant in B. We can have registers in B. We can use direct addressing for B. We can use direct addressing for A. If I'm going to use a constant, I can only have one constant, right? You understand? The other one has got to be a variable. Everybody understand that? Did I say that about the add? Okay, so this is subtract. Okay. So this is a subtract instruction, and they're using direct addressing, right? But this don't have to be, right? They could be a what? They could be a constant, but one of them's got to be a what? A variable. Multiply. Got 3 operands, source A and source B, and then we got to put it what? Got to put it somewhere, right? Good guys. So this is an example of a multiply instruction. Multiply, you got to be real comfortable. You can exceed this range real easy in multiplication, right? Now in your lab, we're not going to do any big numbers. As long as I'm dealing with a number, that's lower than 65,536, you might get an overflow on your sign numbers, but you can still use it, right? Everybody okay? Yes or no? Then we got the divide instructions. Got 3 operands. Source A and source B, right? I think source A is your, what's the column called? The multiplicator. B is the multiplier. And your quotient, you're going to put it where you want to store it, right? Okay. One of the sources can be a constant, but the other one, they can both be what? They can both be addresses, right? You understand? Or one of them could be a constant, but the other one's got to be a variable. Everybody understand that? So this is the block instruction. This is the Allen Bradley block instruction for A. Here they're using direct addressing for all their operands. So what's this going to do? This is going to take whatever's at n:0, n7:0. It's going to divide it by whatever's at n7:1, and it's going to put the answer in this address. Everybody okay? These are the other math instructions. It all depends on what. How many of these other math instructions, what are they depend on? The PLC. So that's what's going to happen when you install in there. It's going to come up here and it's going to say, when you get that, I've got a PLC, but I got Logic Pro up here. So when I come up here and start looking at my math instructions, then this is where it's going to pop up. So PLC, Logic Pro supports what? Add, subtract, multiply, divide, square root. Negate, what do you think negate means? Well, it means to go off, so it would take a negative number and convert it into a positive number, or it would take a what? Positive number and convert it into a negative number. That's called negate. A lot of people think it just goes negative, but negate means to do what? Make it the opposite. Then we got these other 2 guys, TOD and FRD. What are those? Well, we have a big problem. When I do math. When I do math, guys, this is binary math.
You do it or when the computer does it?
When the computer does it, it's binary math. right? Binary. The problem is when I input information into the PLC, I would like to be able to do it in decimal. I don't understand binary and decimal. So we have these thumb wheel switches over here, and that's BCD right there. That's BCD. But if I took that BCD number and told my PLC to add it, it would add them like they're binary. You understand that? So if I enter the 10 on those thumb wheel switches, so if I enter the 10 on those thumb wheel switches, that would be base 10. My PLC would see this as what? 1, 2, 4, 8, 16. So it would see a 10 BCD, it would think it's what? 16 binary. So we need to be able to deal with a decimal world. A binary computer has to be able to deal with a decimal world. So we got two instructions. We got FRD and we got TOD. FRD takes a BCD number and converts it into binary. Does it for you. And then what do you think TOD does? Takes a binary number and converts it into one. Decimal. Well, I haven't quite got this finished yet. Let me take this other one off because I'm using a constant. Now is this, I want to get rid of this. I was working on this. Get rid of this down there.
What does it stand for? TRD?
It's a two binary, we'd have to look it up. I don't think they actually give you the name of the instruction. So this, what I'm doing is I'm coming over here, I5, what's that going to do?
Yeah,
Grab the whole.
Going to grab the whole 16 bits. So this is going to come over and take all this right here. And then what am I going to do? I'm using an FRD, so what's that going to do? That's going to convert whatever comes off the input, even though it's BCD coming off the input, it's going to convert it to binary. And then what I'm doing is I'm coming up here and then I'm storing it in address N7, 0, right? :0. Then I'm taking whatever's at N7, :0, and I'm adding it to the 600. But what I was trying to do is bring in another number from another set of switches, but that's okay.
and then it's put it in
Then, yeah, but then it's going to put it in 7. Then I'm taking the contents of N7 and converting it back to what? BCD, so I can send it to this display over there. So this is a BCD display, right? You understand that? Okay. So what it does is it allows me to input information in decimal. The PLC adds them like they're binary after I convert them, and then I convert them back to decimal so I can use the numbering system that I understand, right? You understand? So over here what I can do now, and we had this problem the other day, if y'all remember, and I told you we could do that. I slapped in a number over here and I told it to do something and it did it in binary, right? You understand that? Because that's what this PLC sees these ones and zeros at. So now what I can do is I think I can run it. I don't think I changed it. Is I can come over here now and enter any number. So I'm going to add it. My constant is what? 600. So right now it's seeing nothing here, but I can come over here and do what? I can input any number y'all want, right? And then I'm going to come up here and hit, oops.
The 209 right now is BCD and 600 decimal, or both BCD?
209 is BCD. So
Right.
these are BCD thumb switches.
Both of them are BCD.
So yeah, look what they go through. If it was hexadecimal, it would go from 0 to F, right? So notice the biggest number I can put is what? 9. Okay. The smallest number I can come up and put is what? 0. And this is showing you exactly what it's giving me. So it's giving me BCD, right? You understand that? This output right here, I think this guy will do hex. You'll very seldom see that, but I don't want it to do that. So what I'm doing is I'm sending it a BCD code and then it's displaying these numbers for me. and I don't understand.
So you're reading from a scale or something like that. Now we
One.
Huh?
Looks like it's input one.
Yeah, but we don't have an input 0 on Logic Pro. We have a input 1, and I've got it normally open, but it don't look like it's working. Yeah, so Logic Pro, your first input module is input 1, and then your second input module. I'm just doing this to load it. We could take this out and do it instantly. Huh? What's that? Not on Logic Pro. Your first input port on Logic Pro is input what? 1. Your second input is input 3. This is not your PLCs, right? In fact, on your PLCs, so y'all telling me something I'm not seeing? I'm using 1.
Yeah.
Okay, there we go.
Yeah.
So what did it do? I input what? 204 BCD. What did this instruction right here do? Converted it over to what? Binary. This added my binary numbers together. This instruction converted it back to what? BCD, so I could display it on the BCD. Right? Y'all understand that? Huh?
I thought you said
No, this is a BCD display. This is a BCD display because I don't understand F, A's, and C's, right? So normally when you look at a display, a numerical display on a PLC, it don't give you binary, it don't give you hexadecimal, it gives you what? It gives you BCD, it gives you decimal, but it's actually, we have to represent that as a code of ones and zeros. And that code we call BCD. You don't even know BCD. All you know is 804. Right, you understand? I don't care how, an operator don't care how the 804 got up there. All the operator cares if I come over and hit this decimal number right here, it's going to give me a decimal answer. That's all the operator cares about, right? You don't care about how your calculator works with decimal. You don't care. All you know is you punch in a bunch of numbers, and when you hit equal, it gives you a decimal answer. Unless you got a calculator that supports programming. And then programming calculators let you deal with the other bases, right? You understand? So on those calculators, if you switch into hexadecimal, then by George, your calculator is going to display your answer in what? Hexadecimal. If you switch to binary, it's going to switch to binary, right? So Windows calculators for years has had that feature. So this is the calculator that's available on Windows 7. Yeah, so right here, this is that calculator. I can go up here into view and I can switch it over to programmers. And now all of a sudden I got decimal, I got hexadecimal, I got binary. So now if I put binary, then my calculator has to do no conversion at all, right? You understand? If I put hexadecimal, then it's going to have to take hexadecimal and convert it into what? Binary. But what do we use hexadecimal for? Does computers understand hexadecimal? No. It understands binary, but it allows the computer to display very large binary numbers with very few digits, right? And what you got to understand, everything you see up here is just a bunch of ones, and it's all dots, right? You understand? And I can take anything and display a bunch of dots up there, and the computer can make those dots look like the letter A. Does this computer understand the letter A? No. We can represent it with a code, right? You understand? And then it looks up that code, and then it's got a pattern. So that's what you do when you download these fonts. It downloads a pattern that when you say I want to display a letter A, it pops the pattern up there for what? The letter A. It don't have any idea what a letter is. But the problem is that the average person does not understand hexadecimal. They don't understand binary. They know decimal. So just about everything you enter into a computer, most people is going to be in what? Decimal. So that computer has to be able to take that code and convert it over to binary so it can do math with it, right? You understand? And then when it's through with the math, what does it need to have the ability to do? Recur it back. one of the things that we used to learn in microprocessors, they didn't have this garbage, and we had to write a machine language program that would take a BCD number and do what? Convert it into binary, and then change it back so we could display it up on the display. And that was interesting. Originally, microprocessors could do two math operations. They could add and subtract. That's all they could do. So how did we do square roots? How did we do multiplication? How did we do, we had to write the actual code for that. But over time, they've added these instructions to the processor itself. So y'all understand? I mean, this is really, really neat. So what it does now, even though the CPU only does binary math, that's all it knows, is binary math. What can we do? We can make that CPU run a program that takes BCD and converts it over to its what? I keep going right past it.
Binary.
Yeah, binary. But then what do we need to do? Convert it back. And that's what this guy does right here. Now, when you enter this instruction, what it does is it does what I used to have to do in machine language. I had to write that program, right? You understand that? But what you do is you call that program. I'd actually have to go back and see how I did that. But we had to do that. We had to figure out how to divide, how to multiply. So we would multiply by repetitive addition. We would just start looping, right? And so if I wanted to multiply 10 times 5, then I would make it loop through the addition what? 5 times. Until my multiplier became 0. As soon as my multiplier became 0, how did I know it came 0? Well, I would check that what? That 0 bit in the flag register. And as soon as it became 0, it means my multiplication was what? Was correct. So what you do is you multiply and you decrement the divide, you decrement the multiplier. Then you do it, and as soon as your multiplier became 0, you knew you what? You know your multiplication was over. Perfect. So FRD, what does this guy do for us? BCD to binary. Then we can use it in all these instructions, all these compare instructions, all these math instructions. We can divide. But then if I need to send that back to you, what do we need to do? We need to take that answer and convert it back to BCD, and then we can send it out to the BCD devices. Is that neat? So now I can come over here and enter any number I want to. And then I'm going to come over and hit the right switch. Can you see what this one does? So what's this going to do? Input 5. Since I didn't specify a bit, it's going to grab the whole what? The whole word, right? Right? It's going to bring that in from an input device. Then what's it going to do? Then it's going to store it out here, because I can't do this directly. I'm going to store this in N7:0. And then I'm going to add whatever's N7:0. I'm adding it to a constant, right? You understand? But what could this be? Could be another input port, right? So if I have another set of thumb wheel switches, I might enter the 2, right? You understand that? So I'm entering a constant. This gives me the hex equivalent, which is okay. Then I'm going to store it where? N7:1. And then what's this guy going to do? Right. Everybody okay? Yeah. So those are the 3 instructions that I think it covers in the book. What else does it cover? Does it cover anything else in the book on the math? We're going to do, yeah, but some of them are very complex, and unfortunately we don't have time to do a lot of the math. I think the way it's set up, let me know. If you got the new lab book, I think it's set up the same. I don't have. I requested a copy, but I hadn't got it. I hadn't got it yet. Oh. So we did, some of y'all are still working on this. We did what? Lab 3, activity 3. Okay. So what's lab 4?
Math?
You did 10?
Oh, I'm sorry. There's no lab 4.
The next one after that comes here.
What's on page 211?
Definition.
But don't it ask you, also ask you to write, to draw out a diagram?
Yeah, this is right. Describe the following fields in math. Oh, yeah, they describe it.
Okay. So why did we do, so this is right. So that's actually lab what? I think I changed it. I think I changed it because I didn't know exactly what was going to be the new lab book when it came out. I think the page numbers are still the same.
This is,
So the lab number is what?
industrial.
And it's activity.
Section is one activity. So actually, well, this is one activity with all, with the multiplication, division, addition, and subtraction.
Yeah, so what we're going to find out is in our more advanced lab, we're going to be able to use these instructions. So just like in the PLC 1, or PLC, the first PLC class, when we started dealing with the logic instructions, what did I have y'all do? The ladder diagram must be drawn to perform each math instruction and specified in the space provided before the description. Create a ladder diagram using RS lot use. So this changes a little bit, right? So that doesn't tell you to create a logic diagram. It just says to draw the circuit, right? Y'all understand where I'm at? And I'll run this off and give it to you. That would be nice, right? And what I've given you is, I've given you page numbers. These I actually give you activities. It says create a logic diagram using RS logic application that is provided in, no, that's not true. So y'all, we used to have y'all do this on on Logic Pro, but the problem is that the new lab book, the new textbook don't have what? No, we don't. No, we've talked about it, but we've never been able to get the money to buy the license. Create a ladder diagram using RS Logic. Name the ladder diagram. Using the syntax, lab 4, first name, last name as an example. John Smith. So the ladder diagram must contain a rung for each of the described math operations. So what you're going to do is you're going to make one ladder logic diagram, and then basically every rung is going to use a different math operation. Does that make sense? What you can do is you can load one of your in registers with the two numbers. We'll kind of do like variables, even though it truly is not going to be a variable. So if you load N70 with a number and you load N71 with a number and you never change that number, then those are technically constants, right? To understand, without changing that. Now, but you see what we can do? We can bring these from where? From anywhere, right? So just do that. So just take one of your N7 registers, load it with two numbers, and then all your math operations, you can work on those two operations. Y'all understand? Yes or no? That makes sense. And so you should have, how many math operations are in that, does it ask you in that lab? 4. So you're gonna do add, subtract, multiply, and divide, right? You understand? Does it say that? We're also gonna include a master start-stop station on this. I think we said, originally what we did is we converted down in here, but I'm gonna go ahead and put this at the top. Cause that's something y'all really need to get used to.
What, putting that mandatory?
Yeah, the mandatory start-stop. What did that say? Oh, I guess I could. So right now some of y'all still working on activity 3, right, on page 189. Some of y'all might be through with that. If you do that, and after lunch you'll come in and you'll start working on this lab right here, right? But what you need to do before you start this lab, you need to do what? Finish the first one. And then I'll go back and check this and make sure that Logic Pro's out of all these. And then I'll post these. Instead of printing them off, I'll just post it up on Blackboard. So that way y'all can get an idea of the labs that we do in this lab.
One, and there's only one activity, but all it's asking us to do is describe the instructions.
Which
Page 211. That's all it's asking us to do is just describe each file.
but then it says, and provide an example for each.
So we're providing the example on
It's- Yeah, we're going to provide the example, but you still need to draw it in there, right? You understand your example. It's just what you're going to do is you're going to create a program with so many rungs, and each rung is going to do a different math operation. Are you okay?
Yes.
Does that make sense?
Time to break.
Yeah, time for break for lunch.
All right.
And where we're going to be after lunch? Lab. And I'll look this over in more detail before I put it up there. I thought I had it, I knew I had it somewhere, but when I opened it up, it was the lab procedures.
Something.